Using 21 additional wires, each memory channel carries an address specifying where to read or write data, and using 7 control signal wires, commands are relayed. The addresses and commands are sent to and shared by all 4 chips on the memory channel, which work in parallel. However, the 32-bit data lines are divided among the chips, and thus each chip only reads or writes 8 bits at a time. Additionally, power for DRAM is supplied by the motherboard and managed by these chips on the stick itself. Next, let's open and look inside one of these DRAM microchips. Inside the exterior packaging, we find an interconnection matrix that connects the ball grid array at the bottom with the die, which is the main part of this microchip. This 2 GB DRAM die is organized into 8 bank groups, composed of 4 banks each, totaling 32 banks. Within each bank is a massive array, 65,536 memory cells tall by 8,192 cells across, essentially rows and columns in a grid, with tens of thousands of wires and supporting circuitry running outside each bank. Instead of looking at this die, we're going to transition to a functional diagram and then reorganize the banks and bank groups. In order to access 17 billion memory cells, we need a 31-bit address. 3 bits are used to select the appropriate bank group, then 2 bits to select the bank. Next, 16 bits of the address are used to determine the exact row out of 65,000. Because this chip reads or writes 8 bits at a time, the 8,192 columns are grouped by 8 memory cells, all read or written at a time or by 8, and thus only 10 bits are needed for the column address. One optimization is that this 31-bit address is separated into 2 parts and sent using only 21 wires. First, the bank group, bank, and row address are sent, and then after that the column address.